Good morning, everyone. Waiting for some more people to walk in or metaphorically walk in. Does anyone have any questions before we get started? I seem to have forgotten to post the notes from last time. Maybe did anybody download the notes from my Google Docs from Wednesday? Also, I seem to have recorded one, but I think that was my nighttime class, but I listed as if it was my daytime class, so I'm not sure what I did. And then I found another one that had an error in it, and I don't know what the heck that was. But anyways, I corrected the error, at least in the written form, but I know it's not correct in the lecture form. How about this question? Maybe y'all can answer this one, since it seems like no one downloaded the document from Google Docs. We covered the AR-15 recoil last time, right? Anyone? Bueller. It's Friday, not Monday. Why are you not replying? Thanks,
I'm trying to pull up my notes real quick.
No problem. Matt, did you say you're trying to pull your notes up? That's what it was. Gotcha. I'm hard of hearing, and now that I've shaved my head again, I'm even less able.
While I'm doing this, trying to get it to load. The midterm is tomorrow.
No, it's supposed to be.
Well, I figured we pushed it to a Monday, but yeah, online it still says tomorrow.
That's weird. I thought I just looked at it and it said the 18th. Maybe I typed it wrong in the actual message, but the deadline definitely does say the 18th. I'm looking at it right now, and it says it'll open on the 18th, 45 minutes before.
Oh, you know what? I'm looking at the midterm or the practice.
Yeah, the practice one I opened that back up because we had some students were unable to take it for various reasons, and it was too hard to figure out exactly which ones were having problems. So I just redid all of them. So if you haven't taken that online midterm practice respondus, then you have until Saturday night at midnight or 11:59 p.m. to take it. So make sure y'all get that done if you haven't already. It looked like most people had taken it, but if you don't take it, then you can't really download the respondus stuff, or you're gonna have to do it at test time. You're gonna lose all your time, and then you're gonna not have the full 2 hours to take your exam. So don't want to do
that. So I noticed that test number 3 was not under the test category, and I was wondering if you meant to do that or not.
There was actually 3 versions of test 3. So who is this speaking? Let me double check. Is this Brandon?
Oh, this is Dylan.
Dylan. Okay. So I think in this class, everybody took theirs on time, but it was supposed to be the one that ends in C and says, this is your second test 3 or whatever. But there's like 3 versions on there. And I took 2 of them and put them outside of the online testing area for the assignments because it's not that category. Those were mistakes. And then the other one's supposed to be in that, but I'll check that right quick while I'm here. Let's see. Yeah, test 03, chapter 5 and 6 _ C. It says this is the corrected one. It has the right number of points. Yeah, that was the right one. Are you certain you actually took it, or do you need to take it? Or are you just worried about the grade not being in the proper place?
I took it and I got a 100. It's just the grade was counted under imported assignment, so it wasn't actually reflected.
Okay, so test 3 was due like a long time ago. You must have taken one of the errant ones.
Well, it said this is the correct one on it.
It did say this is the correct one. I don't even know why it's open then. That's weird. It was supposed to close like on October 10th. So I don't.
No, sorry, I was trying to say that I took it and everything is fine. It's not coming up in the grade book under the test category.
Okay, that might be because well, I did notify some students that like 3 students hadn't taken it and that they needed to contact me. So you might have been in that list. I'm not saying you are or aren't, but either way, I will check into that and I'll send you an email about it after class. Did anybody find their notes from Wednesday? Anybody, please help me. No one? All right, well, it looks like I did.
What was the notes from Wednesday?
Yeah, did you find them, Gavin? I was wondering if,
I joined after you asked whatever you had asked. I was making coffee.
oh, gotcha.
What were you looking for exactly? Conservation of energy?
I think I don't think I posted the notes for Wednesday. So now I went to look back and make sure I did what I did. And I think I did the AR-15 example, followed by some linear momentum and then center of mass. Does that sound right?
I have some notes on linear momentum and a 2,000 kilogram train cart having an inelastic collision with a 4,000 pound cart.
And that was from the 13th.
I didn't put a date on it. I think so.
Okay, that was your last ones, anyways. So I didn't do the AR-15 and some one dimension.
Yeah, I don't think we did something with guns.
Okay, that's cool. I will double check. I mean, I will assume that's right because you're consistently here. So I'm going to go ahead and jump right in this. Anybody else have any questions before we get started?
Could you talk to me about the homework problem concerning the object on the pendulum?
Yes. In fact, I've been helping another student with that as well. Basically, you've got an F pointing to the right according to the diagram, and this is to my my attempt to go to the right. Okay, and the pendulum is out like this at an angle theta 0, and basically when you draw the force, you have basically a tension going up that parallel to the cord. In other words, it's at that angle theta, and then you have an mg pointing down like that, and then you have a purely horizontal force. The problem is when you do that, you could not only lift it, but you could also give it enough energy to get some speed, but you want to avoid that. So what you have to do is set up a statics problem basically. And for any angle theta, show the tension in the rope being an angle theta, show the mg being an angle, straight down, and then show the F being horizontal, and then set up a summation of forces in the y direction equals 0, summation of forces in the x direction equals 0. That allows you to solve for for the actual force that you have to do that work. And you end up getting mg, let me see, that's mg sine theta. So that's what the force is required to that you're going to do that work with. And then you take that mg sine theta, that's the F, and you're going to take that and write it next to I hat and do the integral of F dot dl. And the dl is going to be r d theta times theta hat. I suspect I'm losing everybody. Let me go ahead and show it to you on the document game. So what we have here is a mass M, which I think I should probably write right here. Okay, hanging at an angle. I'm just going to call it theta right now. We know it's going to go up to theta 0, but I'm just going to call it theta for reasons you'll see in a second. I have acting on that a force T, which is the tension in the rope. Then I have acting on it a force mg, which is in the downward or negative y direction. In fact, what I'm going to do is I'm going to draw it right as the positive y direction, or positive x direction, and up as the positive y direction. And you also have a F horizontally. That's why I drew that in green. Okay, so this one is just mg. And if you take the summation of forces in the x direction, summation of forces in the y direction, and set them all equal to 0, which is what you need to do to establish equilibrium, which is the bare minimum force that you could apply F to make it move, then what you'd get is the summation of forces in the y direction is equal to mass times acceleration in the y direction, which we're treating as 0. You can see that this becomes a T in the positive y direction and a T component in the negative x direction. So when I go to do that, I end up getting, for this, The forces in the y direction, as you can tell from this, would be t cosine theta, and then minus mg is equal to 0. So you get t cosine theta equals mg. That's equation 1. Summation forces in the x direction equals mass times acceleration in the x direction. Again, I'm going to set that equal to 0 so I can find the limiting case, the minimal amount of force that has to be there. So in this case, I'm just going to get F minus t sine theta is equal to 0. So in this case, I find that t sine theta is equal to F, and that's going to be equation 2. If I divide 2 by 1, then I end up getting tangent theta is equal to F over mg. So F is actually equal to tangent theta. That's like the minimum force it could be. Or excuse me, times mg, sorry about that. F is equal to mg tangent theta. So that's a way to figure out what your F is. Now your work is supposed to be the integral of F dot dl. Well, dl is basically this arc. So at any particular angle, say here, it should point that way. So dl is just equal to L, the length of the pendulum, times d theta in the theta hat direction. But we know the theta hat direction is negative sine theta I hat plus cosine theta j hat. So when I put this in, I'm going to say mg tangent theta, and that's bothering me for some reason. I thought it was mg cosine, but anyways, we'll figure that out a little bit later. I hat dotted with L d theta negative sine theta I hat plus cosine theta j hat. So you can see the only thing that's going to actually survive is the I hat dot I hat. So we're going to get the mgl negative sine theta. I don't know if I'm bothered about this tangent. Tangent sine over cosine, so I get sine squared over cosine. That's not necessarily good. This is the process that I was going through to do it, but ultimately somehow I remembered getting mgl times cosine theta 0 minus 1. So that's the actual answer you're supposed to get. So I'll at least give you that part. I just for some reason I'm drawing a blank on how I manipulated this, but that's the answer I got for the work done by the force. Turns out the work done by gravity is exactly the opposite. So you flip that and it becomes 1 minus cosine theta 0, and the work done by the tension 0. So hopefully that'll help you enough anyways. I'm gonna put a big question mark by this in case someone sees it on the video, because for some reason I'm not exactly sure.
Yeah, I'll see what I can figure out and I'll come back to you at some point.
Yeah,
Thank
I've been working with a guy in my night class, I believe it is, and I'll see if I can find the notes I sent him, and I'll send that to you. But I do know this was ultimately the answer I got for the first part. The second part was this with 1 minus cosine theta 0. That was the work done by gravity. And the third part, of course, was 0 because the tension is always perpendicular to the motion. So that's why you got 0 force, 0 work by the tension. Does that make sense? All right. Well, let's
Actually,
go ahead.
what was why is it that the work why is it the work done by the gravity is exactly opposite the work done by the force?
It turns out that by taking it from not moving to not moving, you can think about it in terms of the work energy theorem, then initial kinetic energy 0, final kinetic energy 0. Therefore, the total force on, or the total work done on the system must be 0. So you can get it just from the work energy theorem if you want to understand physics case.
Gotcha. Okay.
But you can see, of course, you're also going to in that case, mg points down, so the F would be mg negative mg j hat, and that's going to, of course, take a dot product with cosine theta, because the j hat's the only term that survives there. So that should get you started on the 1 minus cosine theta times mgl. Okay.
Okay.
All right. So here's example 1 for today. So first off, I'll tell you, I'm not trying to make this political in any way. I'm just it's something that comes up in the news and has been for basically even before Columbine. But the AR-15, it's a weapon that was designed sort of as something to make the M16 obsolete. The military ended up not going with, I think it was M16 that was they were trying to replace, but the military ended up not going with it. But it's still a very potentially harmful weapon. It's AR-15, and it does not mean AR, does not mean assault rifle. Okay, there's not really a really good definition of quote unquote assault rifle, so don't think I'm taking that tack. I'm just saying that AR-15 is a weapon that's in the news. It has a mass of about 6.55 pounds, which is 2.97 kilograms. And it fires the Remington 223, which no one writes this way. They just write 223 Remington. I think you can see, though, that it's essentially a 22 caliber bullet in terms of diameter, but it's not the typical 22 caliber because they basically put a buttload of explosive inside the shell, and then the actual projectile of the 223, that projectile has a range of masses from 2.27 grams. Whoa. And this is grams, not grains, by the way. Grams to, I think the biggest is about 5.8 grams, but probably the most popular one is the 3.56 gram, also called the 58 grain. Okay, so that's another system of units measuring, but this is it. And it turns out this muzzle velocity for this shell is actually 993 meters per second. So what we want to do is use conservation of momentum, which is really what causes this. We're going to use conservation of momentum to calculate the recoil. So the question is, what is the recoil speed of the AR-15? Now, on a bigger note, what us as physicists are trying to do is trying to point out that, yeah, these movies are cool, you know, when like Clint Eastwood shoots somebody with a big 50 caliber handgun and it hits them so hard that they fly backwards through a wall. The sad part about that is we love that, and it's cool in movies to see that kind of thing, you know, some bad guy getting hit like that, but it's also a little misleading, and it's actually somewhat dangerous. For instance, I actually saw the live video of the poor reporter that was shot in Northern Virginia, and she was shot with a 45 caliber Glock. Might have been a 9mm, but I think it was 45 caliber Glock. And she just, I mean, and she was a petite little lady, and she just kept running. So if you happen to see something that looks like someone might be shooting someone, and you hear click, 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 or pat, 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 that's about all you hear. We're completely distorted from our pictures of movies to realize that that is actually a gunshot, because we're expecting, one, the person to get hit and fall down, and two, we're expecting a much louder clap. The AR-15 will not disappoint in that category. The AR-15 is a loud pop. It's a really impressive pop, and I think that's one of the most impressive things about it for me. So anyways, that's part of the reason why we solve these problems. So what are we talking about with recoil? What we're talking about is imagine the rifle, the AR or whatever. Let's imagine for a second, I'm just drawing a rough sketch, if you will. Let's imagine it's on roller skates with zero friction. If you were to somehow automatically or remote control like pull the trigger of this thing, say, what's going to happen is P initial, which is the momentum of the rifle, the bullet, and anything else, is actually equal to 0 because nothing's moving. So M times V equals 0 is 0 for each of the M's. So that's why. However, after you fire, what's going on is the rifle is moving back with a velocity v recoil, and this little bullet is moving off with a velocity v muzzle. Okay, and that P final is going to be equal to the mass of the AR times v recoil plus the mass of the 2223 times v muzzle. But since conservation of momentum, meaning the net force acting on the system is zero, there's a big force acting between the explosive and the inside chamber of the actual rifle, and between the explosive and the shell, but that's all internal forces. So the real forces acting is maybe this gravitational force pulling downward and a normal force pushing upward. Those cancel out, and maybe a little bit of friction, but that friction should be fairly small on the roller skates, which are assumed massless. Okay, so what that means is P initial is equal to P final, and we set those equal to each other, and you end up getting that the velocity of recoil is just equal to the negative of the mass of the 223 times the muzzle velocity divided by the mass of the AR. Well, we can calculate that. That's negative. The mass of the 223 is 0.00356. Again, that's the most popular one, not the only one. That's the mass. The velocity is 993 meters per second, and the mass of the AR is 2.97 kilograms as well. And you can see the kilograms drop off, and we're only going to have left the velocity. When we do that, that velocity turns out to be about negative 1.1903 meters per second. It's negative because obviously we chose the direction of the bullet to be to be positive. So the recoil is going to be in the negative. Now that's on the order of 2.66 pounds. So that's not that heavy, but imagine, or excuse me, 2.66 miles per hour. I don't know why I said that. So imagine something on the order of, 6.5 pounds being thrown at you at almost 3 miles per hour. That's a little painful, but it's not enough to knock a grown man through a wall. And the AR-15, like I said, it's not that powerful. It is. I mean, the biggest problem, according to the Marine Corps and the FBI, and I think even the CDC did a study on it, is the biggest problem is there's low caliber, the smallness of the shell with the high velocity, it causes it to enter body and then ricochet around and more or less turn stuff into like mush. So that's the real danger of it. But the thing I'm trying to show you is that the recoil really isn't that bad. The danger is, and I've seen this on YouTube videos, people will literally look down the end like this as they're firing it. If you're looking down the end like that and you hold that thing, that's going to be bad. That's a broken nose, a black eye, maybe both. Okay. Alternatively, some people will actually hold their shoulder way out and behind the butt of the gun instead of firmly against it. That's a whole nother problem, because now you're basically going to take that rifle that's coming back at you at almost 3 miles per hour and weighs almost 7 pounds, and it's going to bang you in the shoulder, and it's going to sort of catch you off guard. So it's going to be a large force in a short period of time brought to a stop. So that's going to give you a bruise. So what you're really supposed to do is brace yourself to some extent and put your shoulder right up against the butt of the rifle, fire it, but then allow your shoulder to move back a little bit and cushion the blow, because by doing that, then you're taking the force as a function of time and spreading it out over a larger distance. So you're reducing the actual force that's applied to you. Otherwise, it's going to be a bruising situation. Okay. So again, that's just a physicist trying to, well, I guess somewhat trying to teach you how to properly shoot, but also the bigger thing is just trying to teach you some of the fundamentals of, being careful about firearms, and also noticing, hey, if you're out in public somewhere, because this is obviously something that happens on occasion nowadays, and you hear a crack noise, a pat, pat, pat. Don't think that's not a gun, because it don't sound like a gun. That is very much what a gun sounds like in person. If you're right up against it, it sounds much louder, of course, but out in the public, in the open, where nothing can ricochet and bounce off and come right back to you really fast, it's really quiet. And two, don't expect people to go flying across the parking lot when they've been hit. And in fact, they might not even fall. So that's one example. And we're going to return to that in a second when I study a ballistic pendulum. Let's turn to another example. And this example is a little big for the bottom sheet of paper here. So I'm going to do a whole nother example on a whole nother page. So this is example 2. And this is a head-on one-dimensional problem. This is a one-dimensional head-on elastic collision. Okay, so that's the nature of the problem. We can imagine it as if it's a ball of mass MA moving with velocity VA towards a ball of mass MB moving with velocity VB. And then after the collision, maybe VA prime is the velocity after the collision of MA, and maybe MB has a velocity VB prime after the collision. Okay, so what we write is conservation of momentum, which, by the way, this is given as equation 9.3 in your text. So it's definitely one you're allowed to copy on your equation sheet. Obviously, we don't need it for this test for the midterm because that's too many. That's a chapter that's not covered. So I'm going to write MA VA plus MB VB is equal to MA VA prime. This is all one dimensional, so that is a vector equation. In fact, it'll come out positive or negative depending on the directions. And then plus MB VB prime. Okay. So that's equation 9.3, which I'll manipulate, and I'm going to manipulate it in a way that I've learned from experience and you know, teaching this class for years, and also as a student, I've learned the best way to write this is what I call equation 1, and that's getting the MAs on the same side. So I'll factor out a VA minus VA prime, and then I put the MBs on the other side, so I get an MB, and in this case, it's VB prime minus VB. Because you can see the VB prime is positive on this side, and this will become negative when it gets over there. So that's a good version. And that's just me knowing what to expect and knowing a good way of solving the system. Now, the other equation, since it's elastic, that means momentum, kinetic energy is conserved. And this is equation, I think 9.7 is what I wrote in my notes from your textbook. And that is 1/2 MA VA squared plus 1/2 MB VB squared is equal to 1/2 MA VA prime squared plus 1/2 MB VB prime squared. Again, I know a smart way to write this, and I'm going to call it equation 2. But first off, I think you can see that there's a common factor of 1/2 that I can go ahead and get rid of. It turns out a good way to write this is MA times VA squared minus VA prime squared equals MB times VB prime squared minus VB squared, like that. Believe it or not, that's not the best way though. In fact, I'm going to write it now using my knowledge of factoring, and I'm going to call this equation 2 prime. So I'm going to write MA VA squared minus VA prime squared as VA minus VA prime times VA plus VB prime, or excuse me, plus VA prime. So that's an A there. Let me go ahead and erase it, make sure it's obvious that it's an A. You see what I did? That's just the difference of squares factoring. So here's MB. And I'm going to do the same thing with it. I'm going to say VB prime minus VB, VB prime plus VB. And now I'm going to divide 2 by 1. So I'm going to put the MA VA minus VA prime under it, and the MB VB prime minus VB under it. Someone else just came in, let me admit them. So you can see that the MA and the VA minus VA prime is going to cancel out, and the MB and the VB prime minus VB is going to cancel out. So all I have left is just this nice little expression, VA plus VA prime is equal to VB prime plus VB, which is good, but it's not the way I'm going to leave it. In fact, the way I like to write it is this. I will say VA minus VB. In other words, the difference between the two velocities before collision is equal to the negative of the difference of the two velocities after collision. See how the orders now change to be exactly the same? So that's the key result that I really wanted. In fact, your book considers this valuable enough that it labeled it equation 9A. Again, your book's using different notation, and that's because, you know, I'm just making this up as I go, just from years of experience, as opposed to copying it from your book. So that is a conclusion that we can make about one-dimensional head-on elastic collisions. Whenever we have one-dimensional head-on elastic collisions, I can use this result. Now, what I'd like to do is apply this to a specific problem. So I found a result, and I didn't really, you know, I called it an example, but I didn't really state what I was trying to figure out. But generally speaking, a momentum problem like this is all about you knowing the initial masses and velocities and wanting to know what the final velocities are. So this is a way, one way, of course, where I can relate the final velocities to the initial velocities. So in some sense, I have a valuable equation, but I haven't completely solved it. And to completely solve it, I'm going to make special considerations. So for instance, I'm going to say, let's consider a problem where we're doing two pool balls in a head-on elastic collision. The reason why I do that is two pool balls are essentially the same mass. So our example 3 is going to be two pool balls in a head-on 1D collision. I don't know why I made an F there. Long time since I wrote in cursive, I guess. So two pool balls. In head-on elastic collision. So that means MA is equal to MB is equal to just plain M. So when I do this, what I can do is make use, for instance, of this equation, and I can make use of the actual conservation of momentum. So let me write down the conservation of momentum again. Conservation of momentum, since they all the same mass now, is MVA plus MVB equals MVA prime plus MVB prime, which clearly means you can cancel out all the M's to get, you guessed it, VA plus VB equals VA prime plus VB prime. So I'm going to call this equation 4. Now you can see if I add equation 3 and 4, look what happens. You can see the VA added with the VA gives me 2 VA, but then I have a negative VB added with a positive VB, so that's going to give me 0. Then I have a negative VA prime added to a positive VA prime, so that's going to give me 0. And then I have a negative negative, that's a positive VB prime added to a positive VB prime, so I get 2 VB prime. So that ultimately tells us something new. That tells us that VB prime is actually equal to VA. So it looks as if object B just exchanged velocities with object A. So that's one new result we hadn't had. Now, if I wish to take this and plug it back into my conservation of momentum equation, I can find out what VB prime is. So I'm going to do that. I want to say VA plus VB is equal to VA prime plus, now instead of VB prime, I'm going to write VA. You see what happens if I subtract VA from both sides, that becomes 0. And lo and behold, what I get is VA prime is now equal to VB. So in fact, it's a complete trading of the velocities. So let's look at a specific scenario in which that occurs. I'll call this example 4. Okay, let's imagine I have the cue ball moving at 5.00 meters per second. And then I have another ball moving at 2.00 meters per second. This is before. And then after the collision, what this is telling me is that now the new velocity of A is going to be the old velocity of B. So now I have the cue ball moving at 2.00 meters per second, whereas the other colored ball is now moving at 5.00 meters per second. So that's an actual conclusion that could happen. Let's look at another scenario. Let's imagine this one. I'll call this example 5, say. It looks like I'm writing outside the page because my calculator's in the way. Example 5. Now let's imagine this ball moving at 5.00 meters per second, and this ball V equals 0. This is before. And then after, according to our equation now the white ball will be sitting still. And the other ball, which this is probably something you've experienced yourself several times, will now move off at a velocity of 5.00 meters per second. And this is after. So that's probably what you're used to seeing when you're playing pool is you hit the cue ball runs into the 8 ball, then the 8 ball takes off with about the same speed that the cue ball had. So this does match our everyday life experiences. And in that sense, we're, happy about it because it's doing something that we've seen in reality. So in some sense, we already have experimental data on it. Any questions on that? All right, now what I'm going to do is try to solve generically. This will be example 6. Now I'm going to try to solve generically a collision between two unequal masses, again in one dimension and elastic. Somebody else try to come in. So this is going to be, like I said, example 6. I've started numbering the examples specifically so it's easier for you guys to refer to. So this is example 6, and I have unequal masses. It's head-on. It's elastic. And one is sitting still. So we basically have a scenario like this. Okay. And what we want to do is work it out. And I want to know A, VA prime and VB prime. B, I want to know what that means for MA, much, much bigger than MB. And C, I want to know what that means for MB, much, much bigger than MA. Okay. So again, we're going to make use of some of our equations. We're going to, for instance, start off with conservation of momentum, and that's going to be basically that MA VA is equal to MA VA prime plus MB VB prime, which we can make into MA VA prime minus, or excuse me, VA minus VA prime. So in other words, I'm trying to do the same thing I did before to get that special equation. But the other side is just going to be MB VB prime. Okay. Now I can take my kinetic energy, 1/2 MAVA squared is equal to 1/2 MAVA prime squared plus 1/2 MB VB prime squared. And that's going to give me MA times again VA square, or excuse me, VA. I'm going to go ahead and skip a step and do the factoring. So it'll be MA VA minus VA prime times VA plus VB prime, or VA prime, is equal to just MB VB prime squared. So basically I did the same thing I did over here with get all the MAs on one side, and then I factored it because it would have been VA prime squared, or VA squared minus VA prime. Again, I really wish I could erase it a little better. There you go. Now, if I take this equation and divide it by that one like we did before, then you clearly see the MA and the VA minus VA prime are all going to cancel out. And I'll just get VA plus VA prime is equal to MB, and MB is going to cancel out. And one of the VB primes is going to cancel out. So I'm just going to get VB prime. So that allows me to make a grandiose statement. I can solve for one of the primes in terms of the other. So anywhere I have an equation with both primes, I can make it now an equation of one variable. So what I'm going to do is I'm going to write VA prime is equal to VB prime minus VA. So I'm going to take this as a valuable equation. I'll label this 1, this 2, and this 3. Okay, now what I'm going to do is put 3 into 1. So when I put 3 into 1, notice what happens. I have MA times VA, which is just VA, minus MA VA prime. But VA prime is going to be VB prime minus VA. And then the other side is just MB VB prime. So now you can see the only unknown in this equation is VB prime. So I can manipulate that a little bit. First, I'm going to go ahead and distribute this. So I got MAVA minus MAVB minus minus, it'd be plus MAVA equals MBVB prime. So I can see what happens here. The MAVA add up to give me 2 MAVA. And over here, when I pull this to this side, that becomes positive. So I get MA. Oh, this should be equals here. Sorry. That becomes an MA plus MB times VB prime. So lo and behold, I get an answer that looks like part of the answer from the Atwood machine, the tension specifically in the Atwood machine. So that's a nice way to remember it. What we've now found is that VB prime, the velocity of the thing that was sitting still, but now after the collision, is in fact 2MA over MA plus MB. And that's all times VA. So that's a general result. That's a result of a head-on collision in which one object was sitting still. And it's not as unuseful as you might think. You can always, no matter what the velocities are, you can imagine a reference frame in which one of them is not moving at all, and then all these equations are valid. And then if you want to know the results, you switch to back to the original reference frame. You know, and I say reference frame, I mean like a coordinate system moving along at the same velocity as VB, or excuse me, MB. So that's the velocity of the one that was sitting still, but after the collision. Now, if I take this equation, which I'll call equation 4, if I plug that into 3, what I'm going to get is the following. So I'm going to plug it into 3. And of course, 3 was our VA prime is equal to VB prime. So I write 2MA over MA plus MB. Now that's times VA. What I have over here is another VA. So I have a common factor of VA. So I'm going to go ahead and factor that out. I'll put parentheses here, leave a space there, and put VA. Of course, what goes here is 1. But I know I need a common denominator, so I might as well write 1 as MA plus MB over or under MA plus MB. When I do that, I can see, remember your fraction bar is treated like parentheses. So this minus distributes to both of those. So now I have VA prime is equal to, notice I'm going to have 2MA minus MA. So that's just plain MA. And then I'll have minus this, that'd be minus MB, all that over MA plus MB, which looks exactly like the Atwood machine equation for acceleration. So that'll be equation 5, say. And this is a result that you can derive. I can't remember if the book actually have these numbers. I'm pretty sure they don't. So that means you'd have to derive it if I asked you to. But if they have it labeled like 9-10 or something like that, then you can use it on your equation sheet. What I'm reminding you of is that the tension in the Atwood machine was 2M1 M2 over M1 plus M2 times G. See, the difference is I got an extra factor of mass there, but that would have to be the case for you to have the right units for tension. And what the Atwood machine, in the case of the acceleration, was M1 minus M2 over M1 plus M2 times G. So that's what I use to remember that. If you ever, if you're forced with a scenario in which you have to derive it, at least you can remember what the result should be. So that's part A. We now have part A solved. Now part B, we want to know both of the velocities in the case of MA much greater than MB. And we only got like 2 minutes left. So MA much greater than MB could be treated as VB prime is equal to the limit as let's say MB over MA approaches 0. Now I'm just going to write the expression, which would be 2MA over MA plus MB. And of course that's times VA. But if you want to actually make use of this limit, what you need is MA to be in the bottom. So what I'm going to do is multiply by 1 over MA over 1 over MA. When you do that, you'd see that this becomes 1 plus MB over MA, and this is just going to become 2. So in the limit as MB over MA approaches 0, we just get 2 times VA. Now that's a big deal. Okay, what that means is you're sitting still, and I'm trying not to get gruesome here. I've had some people in my life experience these kind of things, so we'll just keep it simple, like a bug. Let's imagine a bug that's not so well. It's Iron Man bug. Let's think of an Iron Man bug. Okay, he's got to be so structurally sound that when he gets hit, he doesn't just splat, right? So what just happened was we had a Mack truck with a vertical windshield run into a Iron Man fly. The Iron Man fly, of course, ended up shooting off. If the Mack truck was moving 60, the Iron Man fly would move off at 120 miles per hour. That's what's so deadly about big vehicles hitting small vehicles, or big things hitting small things. If you want to see what happens to VA, you do the same thing. So VA prime is equal to that same limit, only this time it's MA minus MB over MA plus MB. Again, we're going to take the limit as MB over MA approaches 0. And again, I got a VA there, but to implement this, I'm going to divide by 1 over MA over 1 over MA. So you can see in this case, it's going to become 1 minus 0 over 1 plus 0. So it's just going to be VA. In other words, the Mack trucks are not going to slow down. The bug's not going to slow them down at all. So finally, let's do part C, and that's MB much, much greater than MA. In that case, we're going to do the same thing. We get VB prime. I'm a minute past time. We do not have lab for those of you who had me for lab. We're not having lab today. I think I sent that email out already. So there's no lab this week. You're going to owe me those hours later, and you're going to do them on your own. And it's on a mother of all labs. But let me quickly do this. I'm going to take the limit, and this time it's going to be as MA over MB approaches 0 of 2MA over MA plus MB. So you can see this time you're going to multiply by 1 over MB. And of course, this would be MA over MB approaching 0. So what you find out is that this is approximately 0. And then when you do VA prime, what you're going to find is the same limit is going to be taken, but this time it's MA minus MB over MA plus MB. Again, you could make that fraction like you want it. I'll just put a dot, dot, dot to refer to that. You can see in this case, you're going to have MA over MB, which is essentially 0. And then you're going to have minus 1. So I just get approximately negative VA. In other words, you're going to bounce off of the object. If the fly runs into a Mack truck, it's going to bounce off the windshield of the Mack truck and go exactly the same speed in the opposite direction. And we use that often when we're modeling atoms and molecules as perfectly elastic collisions with the walls of the containers. So that'll come up later when we do thermodynamics and kinetics or kinetic theory. So that's it, everybody. Next time I will go over center of mass. I'll do a 2-dimensional collision problem and we'll be done with chapter 9. So you guys are free to go. I'll wait for the last person to leave in case you have any questions.
What is that on the second line? It's VB equals 0, or like
This one right
so it's
here?
VB prime. No, second last line.
Yeah, okay. VB prime,
prime.
is approximately equal to 0.
Yeah, well, that equation, it's 2 mass A over mass A plus mass B times velocity A.
Yeah, it's that equation.
Okay. So MA over MB. Oh, so basically you're saying that because MB is effectively infinitely large, the result comes out to 0?
Yeah. So yeah, if you hit a giant concrete building with even a Mack truck, the concrete building's not going to move.
And what is the VA prime again?
That's
VA
the velocity
prime
of the thing that was actually moving. That's the velocity it has after the collision. Now you don't normally
and this
see
is a perfectly elastic collision?
Yeah, this is an elastic collision. So when you crumple up a car in a wreck, that is the antithesis of an elastic collision.
That's inelastic because all the energy is being expended into crumpling the car.
Exactly. So that's why you don't see that, but you sort of see it in pool. If you hit something at a bumper, it generally comes back out with the same speed. If it's got a little spring to it, it can do even more, or at least the same.
Did you get my email, Professor?
This is Cavian.
Mary.
Is it Kat?
No, it's Mary.
Oh, Mary Perez. I did get your email, but let me see. Maybe I didn't read it. I remembered seeing your email come up. Is it something private or is it something you're willing to tell me right now? Because I'm looking for it. I remember seeing your email, but I don't remember answering it.
Yeah, I would just want some help on propagation and stuff.
Gotcha. Yeah, I can help you.
And also, thank you. If you have any free time today, I guess just give me an email. I don't know if you have any other classes.
I have time right now if you need. Or if you wish.
Yeah, if afterwards you want to log out this class and we can just go into
Propagation
whatever private office hours you have.
Yeah. Yeah.
I think I'll hop in on that actually.
Okay, Gavin wants help on that too. All right, well, let's go ahead and ask whatever questions you might have. Go ahead, Mary. Anybody else have any other quick questions before Mary starts? It looks like there's only 2 of you left in here, 3 of you left in here.
Well, I was actually gonna sit down with you and go through the last lab so I can better understand propagation, so I know how to do the mother one.
Okay, gotcha. So let me set it so you can share the screen. And you're talking about the propagation of error lab, or you're talking about the linear graphing too?
Error propagation.
Okay, error propagation. Go for it. Are you posting it, Mary?
I'm thinking about how to word my question because I'm just kind of lost. I just need to go through it.
Well, the good news is when I do the mother of all labs, I'm going to, explain the lab and then explain to you exactly what you're going to do. And I'm even going to give you the formula. So it sounds like the mother of all labs, but it really is just applying a bunch of formulas. That's the only danger.
Yeah, I had a lot of trouble following all of the math in the first part of this lab here.
Yeah, and the stuff about standard error, standard deviation, that stuff is just statistic stuff. And I've given you I guess it's somewhat of a heuristic argument in that paper about what we're doing and why we're doing it. All you really got to do is just say, oh, well, these are the formulas I'm supposed to use, and that'll work great. Later, you'll have probably an intro to statistics class, and then maybe even a calculus-based statistics class where you'll know better about how these things come about. It's just, this is another instance where you're learning your math from a physics instructor.
Yeah, so I mean, I just didn't understand. Like, I was watching the videos and you said, like, we had to make another version of this table, except you wanted it on Excel.
Or your calculator, either one, or both.
Yeah, I don't know how to do that.
Okay. Yeah, so you don't know how to do it in Excel, or you don't know how to do it in your calculator?
Well, I have a graphing calculator, but I don't think it does.
Which calculator do you have? Do you know it off the top of your head? Is it TI or a?
It's a TI 83 plus.
Yeah, TI 83 plus can do it. You can do a Google search for TI 83 plus statistics, and there's a ton of videos out there that'll show you how to do it. You can learn from the actual manual, which you can also do a Google search for. That's the way I learned mine on my HP. But basically, there's a way you can set up a matrix or a table within your calculator, and then you just tell it to do statistics on it. It'll spit out the standard deviation, and it'll spit out the mean, the max, the min, and usually the sum. So it actually would fill in that sum row right under HCM. It'll fill out that average row under HCM, and then it'll fill out that standard deviation row, which is under H minus H bar squared to the left of standard deviation. Then all you have to do is take the square root of 6 and divide that into the standard deviation, and that would give you that standard error down at the very bottom. So Excel does the same thing.
Can I see you do some math on your screen? Because like
Yeah.
I still don't understand like this.
Yeah, so let me pull up a Excel document. So I'm pulling one up now. Okay, let's see. I don't see anything. I'll just do a blank workbook. And now I'm going to go ahead and share that screen with you as soon as it opens. So I'm going to get you to read off those numbers for the H. Hey, can you read off those for me?
Oh yeah, sorry, I was muted.
No problem.
56.4, 56.38, 56.38, 56.41, 56.4, and 56.39.
56.39, is that what the last one was?
Yeah, that was the last one.
Okay, so 1, 2, 3, yeah, that's all of them. Okay, so I had under that the word sum. Actually, I had to the
Is
left.
that literally just adding them all together?
Yeah, so that's just, you know, the mathematical term for sum them all up. And lo and behold, Excel does sum.
Oh wait, hold on, let me switch to your screen. You just write equal sum.
Yeah, and then
And
I just
highlight.
highlight the column.
Okay.
At this point, I could take that sum and divide it by 6, because right here it says average. So I could do equals this divided by 6. Oh man. What? Oh, no wonder I hit equals instead of divided by. So that's the average, 56.393. But I could also do equals average. Again, typing B3 through B8, and I get the same thing. Now I'm going to do H minus H bar. Oh man, what did I do there? I have a stupid mouse pad on this laptop I'm using. I hate it. I always touch it by mistake, and it moves my cursor to somewhere it's not supposed to be. This is H bar, and it's in centimeters.
Okay.
Okay, so I'll make this a little wider so that word fits there. So I'm just going to do equals this, excuse me, minus that.
Oh, I think you put equals twice.
Equals again, dang it.
Yeah.
Okay,
No
so
worries. I'm using my laptop too, so I'll probably do it a couple times.
so I just copied that down. Whoa, wait a second. Know what I did? I was supposed to be subtracting B10, but I forgot to put my $sign there.
So it's the H minus the average.
Yep, and that's called just the deviation. Or there's some other terms for it, but basically it's just the difference between the two. But it turns out when you average that, you actually get 0. You could actually do average right here, and you'll see that it comes out to be 0. But I'm going to do is square it though. So I'm going to say this squared. In other words, instead of writing all the crap, I'm going to say equals
Yeah.
the 2.
So that's equal to the H bar, and then you really just put squared. Okay.
Yeah. Okay. Now I'm going to say equals sum, because that's part of my formula for the standard error. I mean, for the standard deviation, is these deviations squared. I take the sum of that. Now, I don't actually take the average. I do take the standard deviation. So I'm going to say,
That's weird. It's still the same as the last one.
let's see what I got. Equals, no wonder, sum. Supposed to be all of those. Thanks for catching that.
Yeah, no worries.
Okay, so that's the sum of the squares. Now, the standard deviation formula says you take that number, x minus x bar, in this case, h minus h bar squared. You take that sum and divide it by not n, but n minus 1. So I'm going to do this is equal to the square root, square root of this divided by 5. Excuse me. And that's my standard deviation.
I'm sorry, can you say that one more time? I was writing too.
So the formula
X-
says the square root of h minus h bar squared. Take the sum of all those and then take the square root and divide it by n minus 1. Actually, that's when you take the square root. So what I just did is took that sum and
that was right above it.
yeah, and divided it by n minus 1, which n is 6. So that's 5. And then took the square root. So that's my actual standard deviation. But the reason why I'm getting you to do it on here is you want to make sure that that's the same formula that Excel is using. So you can just do this, copy these over and see if I get the same number. And it didn't. I think I know why I did this error earlier. Let's see, D3 to A3. That's right. Oh, no wonder. That's why. The standard deviation should be of these numbers. Ah, dang it.
Okay.
Friggin' mouse pad.
Oh,
Like a baby.
let me check that worksheet.
There you go. So you see that the standard deviation package that Excel has gives you the same thing.
Okay, could you just can you click on those three
Mhm.
really fast? So that's of the H, the standard deviation, regular.
So I was able to follow the instructions as far as what we have right here.
Mhm.
But I think the biggest thing was the significant figures at the end. I couldn't figure out why the measurements were given the significant figures that they were.
Okay, so the rule is significant figures are irrelevant. They're only really helpful for doing in-class homework, basically, or online homework, because then that dictates how many digits to put out, tells you not to round to the end, all that good stuff. In the real science world, what you do is you take any measurement, you make multiple measurements of it, then you take the average, and if different trials had different errors, you take the weighted average. But that's your best value. So that's what goes in front of the plus or minus. Then you take those values again, you take the standard deviation, and that isn't really that helpful either. That just tells you basically what 68% of other experiments like yours are likely to get in their individual trials. What you need is what would 68% of experiments come back with as their result. And that is in fact the standard deviation of the standard deviation, which is called the standard error. So that's the standard error that goes after the plus or minus. And all you have to do to calculate it is once you have the standard deviation, you divide it by the square root of the number of trials. So in this case, I divide this by the square root of 6. So this is standard deviation Excel. If I wanted standard error, then I just take and say this is equal to this number divided by a square root of 6. So that's what goes after the
errors.
minus. Right.
Sorry, can you do that one more time? What
I just took the
just the
standard
square
deviation.
root of the
Yeah, I took the square,
standard deviation?
right. So that's what actually
Divided
goes
by square root of 6.
right. And since we measure this with a meter stick, what we know is that the uncertainty is at best a 1 in the last decimal place, which is 2 decimal places, right? So you might want to, and this is normally what you do, is you take the first digit of the standard error, and that's the digit at which you round. And that takes the place of sig figs and all that stuff. But in this case, this
So 0.
Go ahead.
So it's 0.005.
That's what I'm saying. That's what you would normally do. Oh, yeah, that is the standard error, but this standard error is actually larger than the instrumental error that you had in making these measurements. And you've always got to take the largest of the two. So instead, we're going to report this value as 56.39 plus/minus 0.01. And all that, of course, will be measured in centimeters. The reason being is the uncertainty in the instrument that we use is 0.01. I can't use statistics to make my data better than what my instrument can measure, which is what would happen if I rounded that to 56.393 plus or minus 0.005.
Okay.
Okay.
That might have been what was confusing me, where like it was assuming like rather the correct answer is to take the larger between the standard error and the instrumental error. And because we weren't making physical measurements ourselves, I wasn't really consciously aware of the instrumental error.
Right. That's why I made all that big point to tell you that a meter stick has at best 2 digits that are valuable, and it has to be an uncertainty of 1 in that last digit.
Well,
That's the best.
So two digits where exactly?
2 digits after the decimal place. So you remember a meter stick is cut up into millimeters. So you definitely know the first decimal place because that's marked. The second decimal place is the one you're guessing. So that uncertainty is at least a 1 there. Most people would argue it's even a 2.
So it's millimeters?
That's if you said 3, if you said 563.9, that would be millimeters, but no, this is centimeters. But it's millimeters is the smallest marking, and then tenths of a millimeter are the ones you estimate.
Oh, okay. So if it was like meters, it would go to the 3rd place after the decimal?
With meters, yeah, it'd be 3rd place, yes.
Okay. So for this, you wrote that's just whatever, like the regular. I don't know how to word this. I don't think it actually even asked that question.
So did you get everything off of this? I want to stop sharing my screen and help you with it.
Yeah, I did for sure.
So when you measure something, notice it's obvious whether the end of a measurement is 1.7 or 1.8, because if it's past 1.7 and not to 1.8, then clearly it's 1.7 something. So that's there's no uncertainty in that. That's 1 decimal place. So 1.7 is 1 decimal place. However, I can probably tell the difference between 1.71 and 1.79. So clearly I should be estimating a second decimal place. And that's the way a meter stick's divided up. You should always have 2 decimal places when you use a meter stick, unless it's, you're measuring something that's cattywampus, doesn't have a clear end, like this was worn down or something. That would be hard to tell what the end is or something like that. Generally speaking, you're always going to have 2 decimal places and at least an uncertainty of 1 in the last one.
So essentially a meter stick that has millimeter measurements is going to have an error of 0.1 millimeter.
Exactly.
Plus or minus. Okay.
Yeah. At best case, it can't have any better than that.
Yeah, I think I probably entered an incorrect value for that lab then, because I gave the error as what was it, 0.3 centimeters cubed for volume. Well, I mean, I guess that's for volume. That was something different.
Right. That was, when you actually took the formula and used that, then you have to use your propagation error formula. And again, you round that error to 1 sig fig, and that's the place you cut off your data from. So,
so that was my question. Why round it to 1 sig fig?
You basically, when you say the standard error is, let's say 0.01, that means you don't know the second decimal place except to, plus or minus 1. So you clearly have no idea what the second decimal place is. And because of that, why would you include the 2? Now, that being said, occasionally when that first digit is a 1, we do carry the 1 4, the 1 5, the 1 6, the 1 7, 1 8, because, you know, 1 4, the 4 is a huge percentage of the 1. So sometimes they want to use 2, and then you can round it to that to line up with that second digit. But generally we just use 1. Because it literally says, hey, I'm uncertain by plus or minus 1 in the second decimal place. So whatever I give you in the third decimal place is really stupid.
Okay, you said that like sig figs don't really matter, right? So it doesn't, like, we don't have to round off anything like in that
When
table.
you, like in that instance, I had to round off the average to line up with the first digit of the error. That's where the rounding comes in now. And now if you took those formulas, you know, and multiplied x times y times z, you'd keep all those decimal places until you propagated the error. And then you find out where one digit, where the first digit appears in that new propagated error. And that's where you line, where you round off the volume that you calculated.
Okay, so volume's the only thing that we have to worry about rounding?
No, anytime you use a formula. So anytime you use a formula using real values, like, let me show you, like if you're using x is equal to 3.19 plus or minus 0.02 centimeters, and you're using y is equal to 2.14 plus or minus 0.03 centimeters, and you're using z is equal to 1.17 plus or minus 0.01 centimeters, and your formula is, let's say, v equals x times y times z, then you're just going to multiply these three numbers and get, for instance, 2.19 times 3.19 times 2.14 times 1.17. That gives me 7.9877122. Okay, now you're going to propagate those errors. Well, the propagation error formula for sigma v turns out to be sigma v over v is equal to the square root of sigma x over x squared plus sigma y over y squared plus sigma z over z squared. That's the one we derived. So I'm going to take the square root of 0.02 over 3.19, square that, plus 0.03 over 2.14, square that, plus 0.01 over 1.17, square that. Let's see what we get. So I get 0.02 divided by 3.19. I'm going to square that, add to it parentheses 0.03 divided by 2.14. I'm going to square that, plus parentheses 0.01 divided by 1.17. I'm going to square that. So I got square root of 308.8829 times 10 to the negative 6 with no units. Now I'm going to take the square root of that. Actually, I'm going to learn how to use my calculator and life is going to be awesome. So that is 0.01757506. That's what I got for that. So what I do is, notice this 7. This is one of those weird cases where this number after the 1 is a huge part of the 1. So some scientists might be compelled to go ahead and do 2 digits. So you should report your volume as equal to 7.987 plus or minus 0.0. Oh, excuse me, I got a problem already. What I just calculated there is the fractional error. Okay, the error though, sigma v, is actually v times sigma v over V. Almost made a mistake there. So now I got to take this number and multiply it by the actual volume. So I'm going to say times the volume, which was 7.98 something another. 7.987122. And that gives me 0.1403742. Okay, so that's the actual error, and that comes out in centimeters cubed, by the way. Okay, so now I see I've got a doubtful digit of 1 in the first decimal place, but this 4 is literally 40% as big as the 1. So some scientists would report this as 7.99 plus or minus 0.14, and all that would be centimeters squared. Sorry about how horrible this looks.
And that's 2 decimals because like the X, Y, and Z was 2 decimals after?
No, not at all because of that. It's specifically because we know this one's doubtful, but the person chose to do 2 digits because this 4 is such a large fraction of 1. The other choices, we could have written 7 point, since it was 7.98, this would be actually, if I wanted to do one decimal, I mean, if I wanted to do 1 decimal place and only use the 1 on my standard error, then I have to round this to, if I round the 7.9, that actually becomes 8.0. So I'd have to call that 8.0 plus or minus 0.1 square centimeters. Both of those are completely acceptable, and they had nothing whatsoever to do with sig figs. They had.
Oh, can you spell on your paper a little bit?
Oh yeah, that would help, wouldn't it?
Thank you.
So the important thing, the rounding comes in to either match this like this one did, or if you chose to report, because that first digit's 1 and that second digit is 4 or larger, it would be because you're rounding it to this. See, notice this digit's in the same place as that one. Similarly, this digit's in the same place as that one.
Okay, and it's centimeters cubed, right?
Yes.
I can't tell if it's a 2 or 3.
It is a 2, but that was a dummy on me. But yeah, it's 50 centimeters.
Okay, so I get it. So in the case where up there it was like 0.017, if you'd include the 3rd digit after the decimal point, because it's like a great portion of the 0.01, then I would have to put like.
And I wouldn't take off for you doing that or for you doing it to the 1. Again, it's got to be the actual error though, not the fractional error. But if you did it to 1, I wouldn't take off. If you did it to 1.7, I wouldn't take off. If you did it to 1.3, I probably would take off. If you did it to 1.2, I would take off, but or 1.0, I would take off as well, but not 1.4, 1.5, 1.6, 1.7. You can choose to use 2 or 1 digits in those cases.
Also, isn't 1.3 the same level of discrepancy from 0.01 as 1.7 is to 0.02?
Yeah, it's not that relevant to the to what it's close to. It's more relevant is how big is the 3 compared to the 1 in front of it. 3 is only a third, whereas 4 is 40%. I'd put my line at 40%, and I'm just telling you that's what people do is they normally cut it at 40 or 50%. So
well, yeah, but 40 or 50% in either direction should be relevant, wouldn't it? Because you're saying 0.17 is important because it's kind of closer to 0.2.
No, not because of that. Because the 7, it's not because the 7 is close to 2. It's because the 1.7 is close to 2. It's because the 7.007 divided by 0.01 is 70%. So that 7 is a big fraction of the 1. A 4 over here is 0.004 divided by 0.01. That's 40%. If you do 3, that's only 33.33%, or actually 30%. So I draw the line, and most people draw the line at either 40 or 50% of the digit before it. So they would only do it with a 1.4 or a 1.5 and higher. It's not because how close it is to 2. It's because how big the 7 is compared to the 0.01.
Okay, and so Professor too, like we can leave everything like kind of in its raw numbers except for when we get to the end.
Yeah, the
Then-
final result, you want to make sure you show it as like this, rounded to the proper place. And like I said, I'm not going to take off for you doing this or this.
Because they're both pretty much accurate.
Yeah, you
the
could
same
argue either
statement.
one. Yep.
Okay, that actually helped me out a lot then.
Okay, how about
Thank
you,
you.
Gavin?
Yeah, it helps a little bit. I can kind of see what you're getting at with the 1.7 thing. Still not 100% on the number, basically why, the reason why behind the number of sig figs that you use. Still a little vague on that.
So you do understand though that this is saying the uncertainty in the measurement that you just made, this
Yeah.
is 0.1, maybe 0.14, right? So that means this number could be 7 point or 8.0 or 7.8 if we just accept the one and ignore the rest, right? So if you
Yeah.
know for sure whether that's a 8, a 9, or a 0 followed by a 7, or excuse me, followed by a 7, 7, or an 8, then why do you think you should report that 8 at all? This 8. That's the whole thing. That's why you round it where you do. Because this number is literally telling you, you don't know the first decimal place, but to within 1. If you can't get the first decimal place to any better than within plus or minus 1, then you have no idea what the heck the second decimal place is.
Okay.
I have another
Actually, I
question.
think I can get that. All right. One sec.
The same way we can shorten it, can we also lengthen it? Although it might not be like the best method. Like, so could it be like 7.987 plus or minus 0.141? Let's say we round it up to 3.
Yeah, see, that's suggesting that you've done measurements that are, factors of 10 or 100 times more expensive to make. So suggesting that you know for a fact this error is 0.1403, that's a whole lot of experimentation that has to go on that you didn't do. Really,
That would be
finer
finer line, like being able to, I guess, well, seeing in this case the length, the width, and the height. If we can go farther than millimeters on a ruler.
Yeah, you wouldn't want to. You never. The literal interpretation of this sigma v is that number that you just calculated, the volume using the best values, that number could be 8.0, it could be 7.9, or it could be 7.8. So you're not even sure whether this number is 8.0, 7.9, or 7.8. You definitely can't tell me whether it's 8.01 or 8.02. You can't tell me anything about that. That's what this interpretation means.
I got you. It's just not precise enough. Yeah.
Exactly. So that's why you round it to where you do.
Okay, that's not bad at all then.
Yeah, it's one of those things that you look at and you're like, well, I don't understand that at all. And then all of a sudden you're like, I don't understand how I didn't understand that at all.
Yeah. Yeah, it's like all the math like really makes your brain hurt and you're just like, oh, it was really easy.
Yeah, it's supposed to be.
Okay, so here's another one, Professor, because obviously we have that midterm on Monday. Is it okay if I email you like the sheet or whatever that I make for the formulas and you can tell me if that's
Yeah, if
good,
you want to do
or
it that way, that's
recommend
fine.
putting anything else in there or taking something out, of course.
Yeah, I mean, I'd rather not get into doing that just because that could be a lot of work for me. But as long as you're using equations that have that parenthesis next to it in your textbook, then you're golden. If you're using some other ones, and I've given you a couple cases like conservation of energy equation, then those are okay. But yeah, if you need me to do that for you, I don't mind. It's just like I said, that takes a lot of work. But you got to just make sure you don't copy any ones down there that aren't followed by a bold print parenthesis and number dash number.
You did also say that an equation that is approved in the book and you just rearrange the equation, like to isolate a different variable, that's also fine.
Yeah, that's fine.
Okay, good. That'll just save 30 seconds per question or something like that.
Exactly.
Okay, I think that's about everything then. Thank you.
No problem. Mary, do you have anything else?
No, actually. I think that helped me out a lot. And I'm sure if I do have any questions, I feel a lot more comfortable asking you.
Yeah, no problem. Text me, or that would be the easiest way to make sure I get your message in a timely fashion is by texting me. But other than that, email
Was it
me.
on the syllabus or?
It's on the syllabus. Actually, let me stop recording for just a second.